We are really delighted and privileged to have Scott Aaronson visiting us all the way from Texas. Actually, he was in Davos last week, so he is traveling all over the world. I just wanted to start with a brief introduction to the Black Hole Initiative. For those in the audience that are not familiar, we are the ones that coordinated this presentation today. The Black Hole Initiative is a center at Harvard that is interdisciplinary. It brings together physicists, mathematicians, astronomers, and philosophers. So in a way, it's the only center that I'm aware of that brings together humanities and sciences at Harvard. And the common thread is interest in black holes. And this is a theoretical prediction for what a black hole image should look like that was done about a decade ago. But you must have seen the real image that was on the front pages of newspapers. And that image was produced or advertised in April 2019. It was produced in the Black Hole Initiative as that includes the Event Horizon Telescope team leadership. And so that's the building, 20 Garden Street, next to the Sheraton Commander. And if you were to put a black hole there, that's the way the building would look like. So that's an image produced by Fabio, one of our fellows, which includes the effects of gravitational lensing on the image. So, and the part in the middle is dark simply because it absorbs light that comes from behind. And so today we are very proud to host Scott Aaronson. I should say that I first met Scott in 2007 in Iceland at the conference. And we spoke for hours. It was obvious to me back then that he's brilliant. And he is still brilliant. So whenever you see a young person early on in their career that looks exceptional, just keep an eye on that person. They will go to great heights quite often. And in my mind, Scott demonstrates the supremacy of the biological brain over computers. But today he will talk about quantum supremacy. And he was a week ago in Davos, as I mentioned, schmoozing with all the celebrities over there: Al Gore, Greta Thunberg. I will not mention except some others. And here's hoping that he will stay, an academic for the rest of his life. Even as his celebrity status grows. So I should mention his history. He did his bachelor's degree at Cornell University, 1997-2000. Then did his PhD at Berkeley on the limits of efficient computation in the physical world. Graduated in 2004. And then went for a postdoc at the Institute for Advanced Study in 2004, 1 year, and then after that at the University of Waterloo, 2005-2007, and then he went for faculty positions, first at MIT, and that's the time that when I met him, and then in 2016 he moved from MIT to University of Texas at Austin, to the Department of Computer Science, where he is a full professor, the David Bratton Centennial Chair. And about 6 years ago, he published this book, Quantum Computing Since Democritus, and I highly recommend it for people that are not familiar with the subject. It's a wonderful summary of the various aspects of quantum computing. And obviously Scott received many awards that I will not mention simply because I want to let him speak. I just wanted to mention one anecdote. On his, well, first of all, he has a blog that is quite fun to read. But on his website, he has frequently asked questions. And one of them is, hello, I'm interested in learning about computer science. Please give me some links to get started. And Scott's answer is www.google.com. Scott.
Thank you, Avi, for that extremely kind introduction that I'm sure I won't live up to. And, okay. All right. Yeah, I hadn't even remembered about that FAQ. That was from like 13, 14 years ago. But okay. So it's an honor to be speaking here, and believe me, having spent a week at Davos, if I've learned anything, it's that I am an academic, and I feel much more at home among other academics. And so this talk is called Quantum Computational Supremacy and Its Applications. When I did a Google image search for a quantum computer, that is one of the first things that came up. I don't think that's exactly what they look like. I am a theorist rather than an engineer. But you know, I'm also, I should say, humbled to be giving this talk at the Black Hole Initiative at a place devoted to astronomy, and you know, this is not a subject with an obvious relation to astronomy, but I was thinking about it this morning, and you know, in some sense, what we're trying to do with quantum computation is precisely to explore a space that the laws of physics tell us is there, and that is actually much vaster, exponentially vaster, even than the space of galaxies and stars. This is called Hilbert space. Okay, and unfortunately we can't see it with a telescope. But if all goes well, we could hope to do a computation whose results can only be explained in terms of, you know, the reality of this enormous Hilbert space describing our world. Okay, so that's exactly what quantum computation is about, and that is more specifically what this goal of quantum supremacy that you may have read about in the news in the past few months is about. So that's what I'm going to try to tell you about. Okay, so because, you know, this is a diverse audience, I thought I would take one slide to explain what is quantum mechanics and what is quantum computing. Now, quantum mechanics is not trivial to explain in the space of one slide, but it becomes a lot easier when you do what we like to do in computer science and you sort of take the physics out of it. The way that we think about quantum mechanics in quantum computing and information is that it is sort of a generalization of the rules of probability themselves. If you like, it's an operating system, you know, that the laws of the rest of physics has been forced to run on as application software, you know, for the last 90 years. General relativity, there are some difficulties porting it to this operating system. Okay, but you know, the rest runs on it, and what it's about is about how to, you know, everyone has heard that, you know, God plays dice with the universe, and Einstein couldn't accept it, and blah blah blah. Okay, but the fact that probabilities are involved is not at all the strange part about quantum mechanics. The strange part is what you have to do to calculate the probabilities. Okay, that is the part that is sort of completely different from anything in our everyday experience. So the way I like to think about it is that a classical computer let's, just for concreteness, talk about a computer, has some state, meaning it has some memory, which we can think of as just a string of bits, a string of zeros and ones. And computation proceeds by doing operations on those bits. Like we might say, flip this bit, but only if this other bit is a 1, or things like that, right? Do a sequence of sort of local operations involving a few bits at a time. And even an ordinary computer can have access to a random number generator. It could be some thermal noise. It could be noise in the timer. It could even be quantum mechanical noise. And it could make random decisions, like set this bit to be 0 with probability half, or 1 with probability half. Okay, and if you wanted a vivid picture, you could think of the universe branching in 2 every time that happened. Okay, but so far that would just be a fancy way of speaking, right? You could say, really, this bit is either a 0 or it's a 1, and as soon as you looked at it, you would know, right? But if you don't look, then you can think about your knowledge of it as this mixture of possibilities, which then evolve in time. You could say like all in parallel, and then as soon as you look, then you could say that the state collapses to a single one, because you looked and now you know which one it is. And then you can, by the rules of probability, you can calculate how likely it is that you'll see one string as opposed to another one. So for example, just by summing over all the possible paths that could lead to a certain string of the probability of following that path, which is just a product of the probabilities of making each move along that path. Okay, now, how is quantum mechanics different? Well, a lot of the popular accounts that you'll read about quantum mechanics do not even get as far as differentiating it from what I just said. Okay, but there is a huge difference. There's a reason why people still argue about quantum mechanics, a century after its discovery. And the main difference is that classically, you might say that this bit has a half probability, or a 0, or a 1 probability of being 1. You would never say it has a negative a half probability. Okay, much less would you say that it has an I or a square root of -1% chance of being 1, right? That would just be, what are you smoking, right? Quantum mechanics is based on numbers called amplitudes, which can be positive or negative, or in general, in fact, they can be complex numbers. Okay, and the rules are actually very, very similar to the rules of classical probability, except that they now involve these complex numbers, these amplitudes. Okay, so so a state could branch into what we call a superposition, where say a given bit could have some amplitude, meaning some complex number assigned to it being 0, some other complex number assigned to it being 1. Okay, a bit that can be in a superposition of a 0 state and a 1 state, by the way, is what we call a quantum bit, or a qubit. Okay, the different qubits could be correlated with each other, or what we call entangled. So it could be that if the first qubit is a 0, then the second qubit is always 0, and and if the first is 1, then the second is always 1. This would be in what we call an entangled state. Okay, and to find the total amplitude for some, for let's say a computer, or really any physical object, could be a photon, could be an electron, could be anything, to find the amplitude for it to end up in some state, when you look at it, you have to add up the amplitudes for all of the possible ways that it could arrive at that state. Okay? And if some of the amplitudes are positive and some are negative, for example, they can cancel each other out. Okay, that's what's called quantum interference. Anytime you ever read anything in the popular press about the weirdness of the quantum world, either it's wrong or else it is a way of talking about this interference of amplitudes. Okay, this is sort of this is the trick of quantum mechanics. And now, what are these amplitudes? What do they mean? Well, they are related to the probability that you will see something when you measure, right? In fact, the probability that you see something is just the squared absolute value of its amplitude. Okay, that's called the Born rule, one of the most basic laws of physics that we know. But when you don't look, or when you keep your qubits isolated from their environment, then the amplitudes can evolve by these rules that are not the rules of classical probability. Okay, that involve these cancellations, this interference, that are and sort of they can produce outcomes that we can only explain by reference to amplitudes. And this is how we know that nature was described this way in the first place. Okay, that sometimes, if an event can happen two ways, but they have amplitudes of opposite signs, then they cancel each other out, and then that event never happens at all, as famously happens in the two-slit experiment, for example. Okay, where if light has two different paths to reach a point, then it may never reach that point. And yet if I close off one of the paths, so now there's only one path, well now the light can reach that point. Okay, so by decreasing the number of paths that a system can take, I can increase the chance that it gets somewhere. Okay, that is something that can only happen if I have amplitudes that are positive or negative, interfering with each other. It could never happen by the laws of classical probability. Okay, and but the biggest change, in this new view of the world, is that we put these little brackets around all of our states. Okay, and this is how we remind ourselves that these are quantum states. Okay, this is called the Dirac-Ket notation. And it's just, it is, if you don't know it, it is just a notation for vectors. Okay, these are all just, if you like, unit vectors in some space, and then we're taking complex linear combinations of these basis vectors. Okay, now the idea of quantum computing, in one sentence, is that it is sort of a quantum interference experiment writ large. Okay, so with every algorithm for a quantum computer, you are taking a collection of qubits, you are acting on them by a sequence of operations that can entangle the qubits, make them interact with each other, produce a superposition state, which could now be a quite enormous one, because if I have even, let's say, 1,000 qubits, the rules of quantum mechanics are unequivocal that I need an amplitude for every possible configuration of all 1,000 of those bits. That is 2 to the 1,000 amplitudes, which is more than could be written down, in the whole observable universe. If I, even if I used, one subatomic particle to write down each one. Okay, this is what I meant in saying that, Hilbert space is vast, is sort of exponentially vaster even than the already vast space of the galaxies and the stars. Now, when I measure the computer, the trouble is when I look at its state, I only see one outcome. Okay, and this is the place where almost every popular account of quantum computing that you'll have read goes completely off the rails. Okay, because it just says, well, look, a quantum computer is just like an ordinary computer, except that it tries every possibility in parallel. It tries each one in a different parallel universe or something. Okay, let me explain the problem with that. Okay, trouble is, with a quantum computer, you can create a superposition over every possible answer to your problem, even if there are 2 to the 1,000 power of them. Okay, that's even an easy thing to do. Okay, but if you just look at the computer, not having done anything else, then the Born rule, the rules of quantum mechanics, predict that all you will see will be a random answer. Right? And of course, if you just wanted a random answer, well, you could have picked one yourself with a lot less trouble. Okay? So the entire game with quantum algorithms is to try to choreograph things so that for each wrong answer, the paths leading to that wrong answer interfere destructively with each other and cancel each other out. Some having positive amplitudes and others having negative amplitudes. Okay, like in this example, I have 2 different paths leading to the 0 state, but one has a positive amplitude, the other has a negative amplitude, so they cancel. Okay, whereas for the right answer, I would like all of the contributions to its amplitude to reinforce one another. Okay, if I can arrange that, then when I look at the computer, I will see the right answer with a high probability. Okay? And if I don't see it, I can always just repeat the computation several times until I do. Okay, but you know, the tricky part is you need to get a large amplitude on the right answer. You need to do it quickly, you know, faster than a classical computer could do the same thing. Otherwise, there's no point. And you've got to choreograph all this despite not knowing it yourself which answer is the right one. So, you know, again, there would be no point if you did. Okay, and it is really only for some special problems that we know how to do all of this. Okay, this is what is special about quantum computing, right? It is not just a faster ordinary computing. It is not just some continuation of Moore's law. It is a totally different way of harnessing nature to do computation. It is, you know, this bizarre hammer that nature happens to give you, and the job of theorists in quantum computing is to figure out what nails, if any, that hammer can hit. Okay, so you know, there are many, many different ways that are being explored to actually build quantum computers. You know, as a theorist, I have the luxury of, you know, being totally agnostic, you know, wishing all of them well, and, you know, and just hoping that at least one succeeds. Okay, you know, to me, you know, these are just all different ways of implementing the abstract logic that I was talking about on the previous slide. Just like, you know, to be a programmer, even a virtuoso programmer of classical computers, you don't necessarily need to know how a transistor works, or even that, you know, a computer uses electricity, right? I mean, you know, you just need to know the logic. Okay, it's the same with quantum computing. But the difference is with quantum computing, the analog of the transistor has not been invented yet. Okay, we are, optimistically, we are just now entering the very, very early vacuum tube era of quantum computing. Okay, where we can hope, if all goes well, to do something that is useful. Okay, but you know, it's going to be noisy, it's going to be limited in scale, you know, until we can sort of invent the quantum computing analog of the transistor, if you like. Okay, and there are many approaches that you may have read about that are being pursued. Here at Harvard, the group of Misha Lukin is one of the world leaders in the cold atom approach to quantum computing. There's also an approach where you take ions. These are actually just individual atomic nuclei, which is kind of crazy that you can image them like this. They're suspended in a magnetic field. Okay, the spin state of each one encodes a 0 or a 1, or a superposition of 0 or 1, so a qubit. Okay, you can bring them close to each other, and so they interact. That gives you a 2-qubit operation. And, you know, you have to control them with lasers in a very, very choreographed way to do the exact computation that you want. There's an approach where you use the polarization states or other states of photons as your qubits. There is what's called topological quantum computing, which Microsoft has placed a huge bet on, and which might be ultimately way more scalable than any of the other approaches, but right now I would say is speculative even by the standards of quantum computing. Right? People have not yet succeeded in making even one topological qubit. Okay? You know, all it requires though is to create a new form of matter that's never been seen. Okay? Now, the one that has been all over the news recently, because you can sort of do the most with it right now, is what are called superconducting qubits. Okay, these are enormous by the standards of qubits. They are little, you know, loops of wire on a chip, you know, just the size of a normal computer chip. You know, the loops of wire, you could actually see them with a magnifying glass. Okay, they are, you know, this is what I mean by enormous. Okay, and so they can encode current flowing in 2 different states that represents a 0 or a 1. But what you do is you put this chip in a dilution refrigerator like this, which cools it to about 1/100 of a degree above absolute 0. Okay, and this causes it to superconduct, And what's important about that is that now these bits will behave as qubits. You can get superpositions of the two current states. You can connect the wires together with what are called Joseph's junctions in order to get the qubits to interact and produce entangled states. You can send control signals from a classical computer that is outside of the fridge in order to do a precisely choreographed sequence of operations. You know, I had some business person, you know, visiting Texas ask recently if he could see my group's dilution fridge. I had to explain that we're theorists, so we have a fridge for leftovers, and that's it. But okay, but you know, I do talk to the people who build these things. I even tour their labs if I am sort of, you know, sort of restrained so that I don't break anything. And so why is building a quantum computer so, you know, notoriously hard? Well, the fundamental problem, and this was recognized since quantum computing was seriously explored at all, you know, in the mid-1990s. The fundamental problem is what's called decoherence, right? So I said before that if you look at a qubit, if you measure it, you sort of you force it to decide whether to become a 0 or a 1, right? It collapses to one or the other by this Born rule. The amplitudes get converted into ordinary classical probabilities of being one state or being the other state. Okay, and you no longer have the quantum interference effects. Okay, but now the trouble is, it doesn't have to be a person who does that, or even a cat or a frog or, you know, any living thing. Any sort of interaction between the qubits and their external environment will have the effect, you know, of measuring them. It will be as if the qubits were measured, if the information about whether that qubit was a 0 or a 1 leaks out in any way, gets recorded by the environment in any way. Okay, this is why we don't typically see Schrodinger cats walking down the street. Okay, because, you know, in real life, cats are not isolated from the rest of the universe, right? Anything on a scale where we can see it and it's not, you know, cooled in a dilution refrigerator is probably in lots of contact with everything else around it. And so it's as if all the things we see are constantly measuring each other all the time and forcing each other down to classical states. Okay, this is what's called decoherence. So in order to see that the world is quantum mechanical at all, or in particular in order to do a quantum computation, you need to keep your qubits incredibly well isolated from their environment. Okay, but you can't just isolate them because, you know, because then they'll just sit there and do nothing, right? You have to get them to interact with one another. And not only that, but in an exactly choreographed way. Okay, so that is such a staggeringly hard problem that there have been distinguished physicists and computer scientists who said, this will never work. This can just never be done. This must violate the laws of physics somehow. Now, in the view of most of us in the field, you know, that worry, at least in principle, was answered by a profound discovery in the mid-1990s that was called quantum error correction or quantum fault tolerance. Okay, and basically what the theory of quantum fault tolerance said is that in order to build a scalable quantum computer, you know, that does an arbitrary quantum computation reliably, you do not have to get qubits perfectly isolated from their environment and, you know, and interacting with each other, you know, in a perfect way. You merely have to get them really, really, really well isolated from their environment. Okay, but if they're interacting a little, even if they're interacting a little bit and they're leaking, you know, at some small rate into the environment, you can encode the information that you care about across the collective states of many qubits using very, very clever quantum generalizations of error-correcting codes. Okay, in such a way that even if a small percentage of your qubits leak out, you know, over every period of time into the environment, you can detect that and you can recover the information that you care about from the remaining qubits. Okay, and then just continue on with your computation in principle as long as you would like. Okay, so in some sense, the central engineering goal of this field from the mid-90s to today has been to engineer qubits that are reliable enough that you can use these error correcting codes to simulate qubits that are even more reliable. And then those could simulate qubits that are more reliable still, and so on. Okay, so you want to get to the break-even point where error correction starts to make things better rather than making them worse. Okay, we are, long story short, we are not there yet. Okay, quantum supremacy has not gotten us there. Okay, we're still in a world with no error correction at all. Okay, on the other hand, we are a hell of a lot closer to the break-even point than we were when the experimentalists started doing this stuff 25 years ago. I mean, like, you know, orders of magnitude closer. Okay, so, yeah. Okay, so now what is this quantum computational supremacy? Okay, well, the term quantum supremacy was coined by my friend, the physicist John Preskill, in 2012, and that is basically a way of saying that, you know, if you find this term offensive in any way, then do not blame me, blame him. Okay, so yeah, so it's not, you know, a term I would have coined. In fact, you know, there's been a campaign recently to change it. The trouble is every alternative that's been proposed also has some problems, right? I mean, you know, supremacy, you know, sounds bad, but, you know, quantum advantage, I mean, you know, some people have unfair advantages over other people, you know, I mean, you know, some people suggested quantum inimitability, like inability to imitate, but you know, how many people can pronounce that? You know, others suggested quantum ascendancy, but that makes it sound like we're some UFO cult, you know, waiting to ascend to the quantum computer in the sky, or you know, maybe Oumuamua is a quantum computer, you know, right? So, okay. But all right, let me just say what this term means. Okay, what Preskill meant, and what I will mean by quantum supremacy, is simply the use of a quantum computer to solve some well-defined problem much faster than any available classical computer can solve it running any algorithm that we know. Okay, so it is the, you know, it is sort of, it refers to the moment in history when a quantum computer can first do something that we are pretty sure is classically hard, is hard for existing computers. Now, you will notice that I did not mention useful, okay? So, you know, we are, you know, if we can do something that is well-defined, classically hard, useless, okay, that counts, all right? Now, so think of you know, if you want a historical analogy, think of the Wright brothers airplane, okay? Not a very useful airplane, you know, for commuting, okay? Or think of, you know, a Fermi's nuclear chain reaction, right? Not a useful power generator, okay? But, you know, they were built, you know, solely to prove a point, okay? To prove that, you know, you can do something, that the laws of physics, you know, do not preclude you doing it, and, you know, not only in principle, but even in practice. You can, okay? So, so just to clarify further, you know, while the problem does not need to be useful, we do need to be solving some well-defined problem. Okay, so I will not count it as quantum supremacy if someone says, well, here I have this molecule in my lab that, you know, has some really complicated entangled ground state, and you can't calculate it, you know, with your supercomputer. So I'm going to define my molecule to be a computer for simulating itself, and one that achieves quantum supremacy. Okay, I will not count that. Okay, and the reason that I won't is that I say that in order for something to count as a computer, it has to be logically possible for it to output a wrong answer. Okay, so in other words, there has to be some external standard. Here is the problem that it was supposed to solve, where you can then judge, did it succeed or did it fail at solving that problem. Okay, so simulate yourself is not such a problem, right? You will always, by definition, succeed at that problem. Okay, so basically what this means is we want a programmable device. We want a device that can be programmed to solve a wide range of problems, that have some mathematical definition where we can check the answer, maybe by comparing to nature, or maybe by just doing a calculation on a classical supercomputer, to the extent that we still can, and comparing the results against that. Okay, so now I'm also going to say that we need three things to count as quantum supremacy. Okay, we need an actual observed speed up. So meaning this device you built is solving something much faster as measured in seconds. Compared to the biggest supercomputers that are easily available that might have 1 million cores or something like that. Okay, I will say that I also want a theoretical reason to believe that this is a type of speed up that we would expect from quantum computation. So in other words, that this is, I'm not interested in speed ups that are merely by some fixed factor, like, even if that factor is 1 million or 1 billion, okay? What we're interested in quantum computing, and really in theoretical computer science more generally, is scaling advantages. Okay, so we are interested in solving problems with, let's say, polynomial scaling with the size of the problem, right? Where, with a classical computer, we think you would have needed exponential scaling, right? So we are interested in not just a fixed speed up, but a speed up that gets larger and larger as you go to larger and larger instances of your problem, okay? Until, when you have a problem of size 1,000 or 10,000, you might do something in minutes that could not be done by a classical computer within the lifetime of the universe. Okay, that is the kind of speed up that we are after here. Okay, so we want to know that not just you got this fixed speed up, but it is indicative of an actual scaling advantage. Okay, ideally a polynomial versus exponential scaling advantage. And then finally, we want the first thing to only be explainable by the second thing. Okay, so I want the only plausible explanation that anybody has for this observed speed up to be, well, there was a quantum state that involved quadrillions of amplitudes in a superposition state, and your computer took advantage of that, right? And I'm harping on this because there have been many unfortunately quantum computing is a field like I guess like deep learning, like blockchain, that attracts a lot of excitement. Along with excitement comes a lot of shoddy claims. Okay, and there have been a lot of claims to have already achieved quantum speed ups, even 10 or 12 years ago, and often this was you build a device. There is some quantum mechanics that's in that device. Then again, there's quantum mechanics in everything. It does something faster, like simulate itself. But the case is not made that it's doing the thing faster has anything to do with the quantum superposition state that is there. Okay, so we really want to rule out any alternative explanations. Okay, so the way I like to put it is quantum supremacy targets what for me has always been the #1 application of a quantum computer, right? Okay, so what are the applications of quantum computing people talk about, right? Well, they're, probably, okay, the biggest application, that we think you can really achieve is simulating, physics and chemistry, right? Simulating materials, chemical reactions, and so forth. That's maybe the most practical thing that we know, right? That was the original application that Feynman had in mind when he suggested the idea of a quantum computer in the early 1980s. The application that put quantum computing on the map when Peter Shor discovered it in the mid-90s is that a quantum computer could break most of the cryptography that we currently use to protect the internet. It's not clear that that's a positive application for humanity, okay? But for whichever intelligence agency gets it first, be an application. Okay, and then there are applications to AI, machine learning, optimization that people talk a lot about. It is crucial to understand that those are more modest in nature. The speed ups we expect from a quantum computer tend to not be exponential for those applications, but merely be like quadratic, square root, things of that nature. Okay, but for me personally, and I'll even mention some other applications. But for me personally, the #1 application has always been none of those. It has been just disproving the people who said quantum computing would never work. Okay, and to me that itself is already at least as interesting as, let's say, finding the Higgs boson, finding gravitational waves, since I'm here at the Black Hole Initiative. And if we can also do something useful, well, that's icing on the cake, But the idea of quantum supremacy is let's bake the cake before we put the icing on it. Okay. So okay, these are Gil Pillai, Leonid Levin, Oded Goldreich, Bob Laughlin, Michelle Diakonov, Robert Alicki. So these are 6 very distinguished physicists and computer scientists who have argued that quantum computing would never work. Many of them argued that you would never outperform a classical computer for anything. And that is what Google announced that they did a couple months ago.
Did they change their mind?
Short answer, no. So no. Okay. So by the way, if I were a quantum computing skeptic at this point, in the wake of Google's result, I would simply say, well, look, this doesn't count for anything because you still haven't demonstrated error correction. Right? I would say, we all knew that you could do this, even if I had said that you couldn't do it, a few years before. I'd say, obviously you can do this, okay? But I would say, until you can do error correction, which you haven't, it doesn't scale beyond a couple hundred qubits, and therefore it doesn't count. Okay, that is what I would say. Now, interestingly, Gil Pillai, who is a well-known quantum computing skeptic in our community, that is not at all what he says. He has said that the experiment that Google just did a couple months ago, if it's correct, then it refutes his entire worldview. Okay, it directly targets what he said was impossible, and if this experiment is correct, then it overturns everything he's been saying for 20 years. He has said that therefore the experiment must be wrong. He has been every day emailing the team at Google and copying me to ask for more raw data. He's a pure mathematician, but I guess he's finding someone who knows how to code, and he is going through all of their raw data looking for an error in the experiment, which, in some sense, I'm very happy that he's doing it. That is exactly how science is supposed to work, and it is good that people should try to shoot this result down. On the other hand, I personally would like to optimize not for the good of science, but for being personally right. Okay. All right. So this brings me to the Google result. So you may have seen this fall there were articles all over the press like these. Actually, what happened was that we had known for several years that Google was explicitly targeting this goal of quantum supremacy. Okay, they had a team of about 75 people in their lab in Santa Barbara that built a 53-qubit superconducting chip called Sycamore. Why 53 qubits, you may ask? Well, they built a 54-qubit chip, but one of them didn't work. Okay, so it's been a several $100 million effort. Okay, so like I would say within the last decade, many of the academic experimentalists in quantum computing have been priced out of this market. The academics can do many wonderful things, but it is hard to compete on building a big integrated system with companies that are spending $200 million. Okay, and But they said, we're not going to do science by press release. We're going to, submit our paper to Nature, and so they were, keeping it under wraps. A few of us knew about it. Had to somehow keep it secret, even if we write a blog. Okay, but then what happened was that there were some co-authors at NASA. And so NASA did an internal review of the paper, and by accident, someone posted it on their public website. Okay. Now that would not have, they quickly took it down. It would not have been such a problem, except that Google Alerts then found it. Okay, so Google is just too good for itself. Okay, and so then the Financial Times ran a story about it, and then everyone was running stories. And so then Google was still under Nature's embargo, so they couldn't comment on it. And so then, just sort of because of my blog, I sort of became, unofficial spokesman. They could even, the Google team could route information through me, even though they couldn't comment directly. So, but anyway, the paper did come out a month later. And so then, I ended up, writing all these posts about it on my blog. So, okay, so what does Google, what did the Google team claim to have done? So they built this 53-qubit superconducting chip with controllable nearest neighbor couplings. The qubits are arranged in a roughly square array, and each qubit can, talk to its neighbors, by Hamiltonians, so, by operations that you get to program in and control. Okay, it's a universal set of operations, so if the qubits survive for long enough, then, you could, in principle, you could do anything with them. And then they basically just used this to output samples from some probability distribution over strings of 53 ones and zeros. Okay, so there's some probability distribution D that you are trying to sample from here. And actually, because of the noise in the device, you are not quite sampling from D. Really, you are sampling from a distribution that looks like this. It's 99.8% the uniform distribution. So in other words, just completely random noise. Okay, but it's also 0.2% the distribution that you want, the signal that you want. Okay, it's roughly this. Now that sounds pretty bad, but experimentalists are used to situations like this. Okay, and all this means is that if you want to extract the signal from the noise, you need millions of samples. Now the good news is that this chip is very fast. So once you've loaded on the sequence of operations, then taking each sample can be done in about 40 microseconds. Okay, which means that after about 3 minutes, you can take millions of samples, which is enough to extract this signal of D. That's exactly what they do. Okay. And so then, using a lot of classical computer power, a supercomputer actually, you do statistics on the samples using your knowledge of the exact sequence of operations that was applied to see are the samples that I got slightly biased in a way that corresponds to this distribution D. And then now comes the theoretical computer science part. Okay, because now we have to argue somehow that, well, a classical computer would have had a very hard time to do the same thing, meaning to output samples that were biased in the same sort of way. Okay, in particular, a classical computer, the Google team argued that by the best algorithm that they knew, which was actually one that a student and I published a few years ago, would have taken about 10,000 years. Running on a supercomputer with 1 million cores. Okay, so that's would correspond to a very, very large quantum speedup for this artificial sampling task. Okay, so why are we talking about this weird sampling problem? Why not a more practical problem? Well, the short answer is it's because this is what can be done with the kind of hardware that exists today. But also because if you just want something that you're as confident as possible is hard for a classical computer, then this is actually a very, very, and you don't care about usefulness, then this is actually a very, very good thing to look at, okay? And that conclusion is what emerged from the theoretical work that I and others did on quantum supremacy over the past decade. And so the situation is like this. You know, sort of the gold standard for quantum supremacy would be to run Shor's algorithm to factor some enormous number, let's say with thousands of digits, maybe even a number that protects your credit card number when you ordered something from Amazon. Okay, you know, which yeah, if you didn't know, right? Every time you buy something, you know, you're betting your bank account literally on the belief that factoring numbers is a hard problem. Okay, but the trouble is that requires a full, you know, error-corrected, you know, fault-tolerant quantum computer, which in practice would, you know, the way we know how to do it today would probably mean millions of qubits. Okay, no one is anywhere close to that yet. Okay, and additionally, even if you could do it, you know, mathematicians are not at all unanimous that factoring is a hard problem for classical computers. You know, some, you know, think it's hard, some think it's easy. You know, for better or worse, we base the, you know, security of, you know, the world's electronic commerce on the belief that it's hard. But, you know, there's really no consensus. Okay, so you know, Grover's search algorithm, which gets these square root speedups that I mentioned for combinatorial problems and machine learning problems, that also seems to require a scalable quantum computer. Even simulating quantum chemistry will almost certainly require at least some error correction. Okay. Okay, but there's a different idea that is much more accessible to near-term experiments. As far as I know, it was first proposed in a far-sighted 2004 paper by Terhal and DiVincenzo. The sort of modern push to actually do a, you know, sampling-based quantum supremacy experiment started with two papers in 2011. One was by me and Alex Arkhipov, and it was on a proposal called boson sampling for doing this using a photonic quantum computer, an optical device. The other was by Bremner, Joza, and Shepard. It was for doing it with something called commuting Hamiltonians. Okay, but these, from different starting points, we sort of converged on a similar idea, which was just use your quantum computer not to solve a problem like factoring that has a single right answer, okay, but to solve a problem where the desired output is a sample from a probability distribution. Okay, so, you know, there are many, you know, valid answers. In fact, you know, if your computer is operating perfectly, it will probably never output the same answer twice, right? It is because it's supposed to be outputting samples from a distribution. Okay, but the test of whether it's working well will be a statistical one. Okay, you will do statistics on the outputs that are sampled in order to see, are they biased in the right way towards certain outputs and away from other outputs. Okay, and we will try to, you know, define a task of that sort that a quantum computer can do very easily, but that a classical computer would need exponential time to do. Okay, so so the advantages, first of all, this is way closer to what a quantum computer sort of just wants to do in its natural habitat, if you like, right? Like if you wanted to prove that a chimpanzee was intelligent, you know, maybe you could train it to do arithmetic, right? But, you know, it'll be a lot easier if you just watch it in the wild, you know, doing what it does, okay? So similar here, okay, and the other advantage is that we found that we can get very, at least by the standards of computational complexity theory, we can get pretty high confidence that some of these problems really are hard for classical computers. In particular, in these papers, we were able to prove that if you had an efficient classical algorithm that could sample from exactly the same probability distribution that the quantum computer samples from, then this would lead to what's called a collapse of the polynomial hierarchy. Okay, now if you don't know what that means, you could take my word for it that it's bad. Okay, but you know, if you've heard of P versus NP, it is sort of almost as, staggering as p equals np, but just sort of not quite. Okay, at sort of a higher level up. Now, in the real world, the experiments have noise, and also we don't directly verify what distribution is being sampled. We only, verify that, this test that we applied was passed, right? And so then we have to think harder about, could there be any classical algorithm that would just spoof whatever test we applied, right? And, maybe even by sampling from some completely different distribution. Okay, so then, matters could become more complicated, but still we were able to give some pretty good complexity theoretic evidence that, at least none of the known methods are going to efficiently solve these problems with a classical computer. Okay, the disadvantages, well, until very recently we did not know of any applications for these experiments. And also, there is, when you do these sampling experiments, there is a difficulty with even how do you check the results. Okay, because, we can check the results by just collecting the samples that are output and then doing a computation with our classical computer that will take something like 2 to the n time, where n is the number of qubits. Okay, but what this means is that we could just barely verify that a 50-qubit quantum computer is working correctly. Okay, a 100-qubit quantum computer, it might be working fine, but we could never prove it. Okay, because just the verification would be completely out of reach for any classical computer. Okay, factoring is not like that, right? If you factor a number, no matter how large, it's very easy for a classical computer to multiply the factors together and check that you did it right. But these sampling problems, even the verification is a hard problem. Okay, so briefly, what Google did is, so they challenged the quantum computer by sending it, in this case, a randomly generated quantum circuit on, in their case, n equals 53 qubits. So we have a random sequence of interactions. They are sort of layered in some pattern, like I illustrated here, where, after a few layers, are interleaved, and every qubit is able to influence every other qubit. Okay, and different pairs of qubits can all be interacting with each other at the same time. Okay, and so we fix the pattern of the interactions in order that we can run that same sequence of interactions, which is called a quantum circuit, over and over again on the same qubits, which are, let's say, initialized to the all-zero state. Okay, then we ask the quantum computer to quickly send back a collection of samples from the output distribution of this quantum circuit, call it d sub c. Okay, and then basically we just have to apply a statistical test to these samples to check, are they consistent with having been sampled from this hard distribution. Okay, and the statistical test that Google ended up using is one of the simplest ones that you could write down. They called it the linear cross-entropy benchmark. Okay, and basically all they did is that they said, take each of the samples that were observed from the quantum computer. Now, calculate the ideal probability that you should have seen each of those samples with a perfect quantum computer, using a lot of classical computer power to calculate these probabilities. Okay, add all the probabilities up, to sum them up, and we'll say the test passes if and only if that sum exceeds a certain threshold. Okay, so intuitively, right, the better the quantum computer is working, well, it should be preferentially sampling the higher probability samples, right? And so the higher this sum, the larger this sum should be. Okay, so just to orient you, if we were just generating these strings completely at random, so if we were just totally faking it with just, flipping a coin, inside the dilution fridge or whatever, then we would expect each of these probabilities to be 2 to the minus n on average, right? Because it's a distribution over 2 to the n power different strings. Okay, so I add up k of those, and I would expect to get about k over 2 to the n. So in other words, I would expect to get about b equals 1. Okay, but now what if I had a perfect quantum computer? With a perfect quantum computer, there's a calculation that you can do, which basically says, well, all of the outcomes are exponentially unlikely. right? But some are unlikelier than others. Okay, why? Because some of the outcomes suffered destructive interference. Okay, a little bit more of that, right? They had a little bit more cancellation in all of the amplitudes that led to them. Whereas others of the outcomes enjoyed constructive interference, right? The amplitudes leading to them reinforced a little bit more. And so some of the, while you'll never see the same outcome twice, some outcomes should be twice as likely or 3 times as likely as others. And we can check if we preferentially see those. So it turns out that with a perfect quantum computer, you'd expect to get about b equals 2 here. Okay? Now, long story short, in its experiment, Google was able to get b equals about 1.002. Okay? So you'll notice that is just slightly better than the trivial classical value. It is far from the ideal quantum value. Okay? But if any of you have ever heard of the Bell inequality, or the violation of the Bell inequality, it is very analogous to that. It's like there's a classical value, there's a quantum value, and we just have to, to prove that nature sort of is doing a quantum mechanical thing, we have to prove that we can experimentally achieve a value that is bounded above the classical value, even if it falls far short of the ideal value. Okay, so yeah, so this is the picture I was talking about. John Martinez, who is the head of the Google team, likes to use the analogy of speckle. If I took a laser pointer like this one, and I sent it through ground glass, I would see a pattern like this, where at some places there's more constructive interference. Those are the redder spots. At other places there's more destructive interference. Those are the blacker spots. And so if I just shot a bunch of photons through, I could check, are they preferentially clustered among the redder spots? Okay, except now imagine that this speckle pattern is, not just in this many pixels, but on like 9 quadrillion pixels, representing all of the possible, configurations of this 53-bit string. Okay, so you may have read in the news that even before Google's paper had officially come out in Nature, IBM posted a response paper where, so IBM's initial response was the entire concept of quantum supremacy is wrong-headed because all that matters is solving problems faster for customers, of practical value. And to me that was like, okay, well, yeah, you want to do something faster and useful, but a prerequisite to that is to do something faster, Isn't that obvious, right? But, then they came out with a more robust response where they said, well, actually, we don't think that Google achieved quantum supremacy anyway. Right? I should mention that IBM is Google's main competitor in superconducting qubits. Okay, and so what they said is that, look, if we use Summit, which is the largest supercomputer that currently exists on Earth, which fills the area of 2 basketball courts. IBM installed it last year at Oak Ridge National Lab. That's why they know all about it. And relevantly for us, Summit has 250 petabytes of hard disk space. Okay, and they said, well, using this machine, we could literally take all 2 to the 53 amplitudes in Google's quantum computer, all 9 quadrillion of them, and we could just explicitly write them all to hard disk. Okay, and if we did that, then we could simulate their chip, what their chip did in 3 minutes in only about 2.5 days. Okay, which, you'll notice is a lot better than 10,000 years. Okay, now, it was embarrassing, I think, for the Google team that they missed this, that they were not thinking about just, that ridiculous amount of hard disk space. Okay, on the other hand, I personally feel like, if this is the strongest counter-argument, then, it's kind of like the Kasparov versus Deep Blue chess match, except with the immense irony that IBM is now in the role of Kasparov. Right? So it's like with heroic effort, you can, maybe barely, keep up with what the quantum computer is doing for the sampling problem, using the largest supercomputer on Earth, right? Which, by the way, IBM never actually did it. It's not, this this device is being used for nuclear weapons simulations and stuff like that. You can't just commandeer it for, you know, quantum supremacy research. Okay, but you know, okay, but you know, I believe that they could do it. But even if so, as long as the best simulation is this 2 to the n exponential time thing, then, you know, even if that once they upgrade from say 53 to 57 qubits, that's not going to work anymore, right? You would need, you know, several summits, right? And then with 70 qubits, forget it. Okay, so it's clear that, you know, we've entered a new era where these chips are going to win for this specific task. Okay. So I had a few more, you know, slides that, because I'm running out of time, I think I'm going to skip through. But, you know, we have a lot of the theoretical work that we did over the last decade to sort of set the stage for this sort of experiment. You know, we were in conversation with Google back in 2015 about, you know, what should they do, you know, that would be a convincing demonstration of quantum supremacy. You know, how should they verify that they had done it? And so, you know, we had to think about, you know, what are we confident is hard for a classical computer to simulate, and we had to look at the various algorithms that are, you know, that there are for simulating quantum computers classically that have different trade-offs between their time usage and their memory usage, but, you know, none of them breach this sort of 2 to the n barrier, right? They all just, you know, get closer to it in various ways. Okay. And, you know, we were able to give some theoretical evidence that, you know, at least known classical algorithms, you know, cannot breach this 2 to the n barrier for spoofing this linear cross-entropy benchmark that Google applied. So in a recent paper by me and an undergrad in Austin named Sam Gunn, building on earlier work by me and Weijie Chen, we showed that if there is a fast classical algorithm to spoof Google's linear cross-entropy benchmark, then there is also a fast classical algorithm to take a specific output probability in your quantum computer and estimate it with, you know, a little bit better than random guessing. Okay, so as long as you believe that that is hard, then spoofing Google's benchmark is also hard. Okay, we would love to be able to get better evidence for hardness. Okay, and, you know, so the objection, you know, until very, very recently, the objection was open that, well, you know, okay, you may have proven quantum supremacy, you know, at least modulo anyone thinking of some, you know, extraordinary new classical algorithm for these problems. Okay, but even if so, who cares? Because these are completely artificial problems. They obviously have no applications to anything, right? All you're doing is you're generating a bunch of random bits with tiny biases. This is what random bits look like, if you never saw any. But you know, that's just sort of obviously useless. Okay, and just a couple of years ago, I actually realized that random bits are not completely useless. You know, certainly not if you can prove that they are random to a skeptic. Okay, and that is exactly what you could do by exploiting the tiny biases that are present, that let you pass this linear cross-entropy benchmark. Okay, so I proposed a protocol a couple of years ago that basically says as soon as you can do this sampling-based quantum supremacy experiment, you almost immediately get at least one application from it, which is that you can generate random bits. Now, by itself, that is not impressive. We have lots and lots of ways of generating random bits that are used in practice. But now you could prove to someone over the internet that under some computational assumptions, these bits could only have been generated not only by a quantum computer, but by a quantum computer that sampled the output randomly. Okay? And what is that useful for? Well, that is useful for example, proof-of-stake cryptocurrencies, which are cryptocurrencies that try to get the advantages of Bitcoin, except without using 1% of the world's electricity to invert a hash function. Okay, so they're environmentally friendlier, but what they do require is they require a huge source of trusted random bits, right? Because a lottery is constantly run to decide who gets to add the next block to the blockchain. Okay, and so you need a huge source of random bits that everyone is confident that nobody could secretly bias. Okay, so this is, the kind of thing that this protocol is for. That you would use a quantum computer like the one that Google now has, okay, to, challenge it with circuits that you've generated using a tiny amount of seed randomness. So you've generated the challenges pseudo-randomly. You challenge the quantum computer to respond with, samples that, you can, at your leisure, you can check a few of them, make sure that they pass this linear cross-entropy benchmark. And if they did, then my result says that under some computational assumptions, even a quantum computer could have only passed the test this quickly by sampling strings that had a lot of true entropy in them. Okay, there must be a lot of randomness in these strings, and you can then use a classical tool called a randomness extractor to get nearly perfect randomness that you could then use for cryptographic applications. So Google is working right now with NIST to do the first demonstration of this protocol. This is not by far the most impressive application of a quantum computer, but it might be the only application that is achievable in the next couple of years. So that is why Google, I guess, licensed the IP from us and why they want to do it. So where to go next? I think it would be tremendously exciting to replicate Google's result in other hardware platforms, get better fidelity, more qubits, and so on. This is only the beginning. This is not a done deal. Design new classical simulation algorithms. People should try as hard as they can to overturn Google's result, right? Quantum supremacy is not like landing on the moon. It could be achieved and then unachieved. If someone just invents a much, much better classical algorithm for these specific tasks. Okay, but, on the other direction, we would like better theoretical evidence that the tasks really are hard. Okay, can we get quantum supremacy in the near term in a way where we can efficiently verify the answer with a classical computer? Again, we know how to do that eventually, like with Shor's algorithm and with other, recent protocols that were invented. But can we do that with a near-term, non-error-corrected quantum computer? I think that this has emerged as one of the biggest theoretical open problems in the field. And then there were lots and lots of problems about improving my randomness protocol, making it more practical, and for figuring out what other applications there are for the type of quantum supremacy experiments that we are able to do today. So conclusions. Google has apparently achieved quantum computational supremacy using random circuit sampling on 53 qubits, building on a lot of the useless theoretical computer science that we tried to do over the last decade. Even if true, this leaves the enormous challenges of scalability and fault tolerance, but is already enough to refute those, like Gil Kalai, who said that quantum speedups were impossible. It was thought obvious for years that sampling-based supremacy experiments had no applications. My certified randomness protocol might change that, although a lot of challenges remain in making it practical. Okay, so thank you for listening.
Very understandable presentation. You were very careful to extrapolate just for 2 years into the future.
Yeah.
Now, suppose you increase that interval by a factor of 10, like 2 decades. In your lifetime, what do you think you will be able to do?
Well, I'm hoping to live for more than 2 decades. Well, we'll see. The way things are going, I don't know if civilization will last for more than 2 decades, right? And that, and so when people ask me to forecast quantum computing, I say, I don't even know when, Australia just burned to the ground, right? How much longer will, civilization continue? But, if things work out for civilization, I think, sure, eventually we're going to get all of this, We're going to get fault-tolerant quantum computers, or at least, I would say that is the conservative prediction, right? The burden of proof is on those who think that this is not possible, right? To explain, what is it in physics that is going to prevent it, right? So the burden, is actually on the skeptics at this point. unfortunately, knowing that, people knew in the 1700s that heavier than air flight was possible, they watched birds do it, right? Charles Babbage knew in the 1830s that what we now call, universal computing is possible, okay? But, it took more than 100 years for the transistor to be invented, right? So forecasting amounts of time is kind of the hardest part here. I think that, if someone, was motivated to spend $1 trillion and do a Manhattan Project, I can't say for sure that they couldn't do it, in the next several years. But, the way that things are sort of naturally progressing, I would foresee, certainly like at least a decade of these sort of noisy near-term quantum computers as people try to squeeze some applications out of, what I call the sort of vacuum tube quantum computers, which are going to be inherently limited to probably a few hundred qubits at the most. And, and where they try to get just the beginnings of error correction, right? And then, once error correction is usefully achieved, then scaling up to a truly scalable device with thousands or millions of qubits is a whole further undertaking, on top of that. Now in the past, because of this work that we've done on boson sampling and other things, even though I started like as far as you could get on the theoretical end of this field, I now do talk to experimentalists all the time. And so I've learned how to translate from their language, right? And when they say, absolutely, you can take it to the bank, we will have this in 6 months, within 4 years or so, very often it gets done. Okay, and so that is not right. Which is just another way of saying I do not discount what they say, right? And the things that they've told me could be done, even if it was off by a factor, I'm a theoretical computer scientist, right? What do I care about little constant factors? Okay, if they're off by a factor of 2 or 3, and how long it will take, eventually the things happen. So, if I were able to predict more precisely than that, I think I would not be an academic. I'd be an investor.
Okay, questions?
Yeah.
Yes.
A remark leading to a question.
Yeah.
Remark, there's a very interesting talk this afternoon by Cheng-Wei Liu visiting Harvard for the treatment, Tsinghua University, about a new method for quantum error correction. And the question, in your examples of the hardware, you talked about many things going on in the West, but you didn't mention Japan or the tremendous investment in Shanghai and other places in China, how they're investing billions, not hundreds of millions of dollars. How does that compare to what's going on?
So I would say that in terms of the results that have actually been announced, China is now the world leader in long-range quantum communications, right? Which is a different problem, right? Sending they have the ability to send qubits. Yeah, that's right. I know to send qubits to and from satellites, which the U.S. could have done, considered investing in it, but decided not to. So they are ahead in that area. In terms of integrating dozens of qubits to achieve quantum supremacy, I would say that the leaders right now are Google, of course, and then maybe slightly behind them, IBM, IonQ, Misha Lukin's group, and possibly a few others like Rigetti. There was actually a recent result from Pan's group about boson sampling, which is my baby. So I was very happy to see that boson sampling is still in the race. But the paper that they put out, and this was a few months ago, so the same time as the Google result, and this was with about 14 photons. Okay, 14. So in order to be competitive with where we are with superconducting qubits, you would need to improve that to probably about 60 photons, okay? So, get them all to arrive at the detectors at the same time. So they are not there yet, but I am very happy that they are working on it, and I'm happy, and I as I said, as a theorist, I am in the happy position of just being able to wish success to everyone. So I do wish success to Pan's group certainly in scaling up boson sampling to be competitive with these kind of results.
Other questions?
Yeah.
Yes, over there.
So I'm sure there's a name for this. Do we have enough data to draw a sort of quantum Moore's law of number of qubits integrated?
Yeah, Yeah, so people, if you know, Hartmut Nevin, who is the director of the quantum lab at Google, he coined Nevin's law that says that the number of qubits is increasing exponentially with time, and therefore the difficulty of simulating your quantum computer with a classical computer is actually increasing doubly exponentially with time, right? So that's Nevin's law, and then a colleague of mine named John Dowling said, well, he thought of that first, so that's actually Dowling's law, okay? But, you know, I think, you know, we've got the data points we have are like, you know, 2 qubits, 5 qubits, 10 qubits, you know, and now like, you know, 20, 30, 50 qubits, right? Some people might be comfortable passing an exponential curve through that data. I would prefer to wait a bit longer before, you know, extrapolating.
Last question.
Yeah.
You spoke a lot about the hardware advances, the complexities, but you didn't say much about programming quantum computers.
Yeah.
You know, for most of the people here, we're interested in physical applications.
Yeah.
We know about programming a classical computer. How do you direct a quantum computer to attack the problem you're interested in?
Sure. Well, okay. So you know, that could be, you know, another hour-long talk, or in fact, you know, a whole course that I teach about exactly those questions. But you know, so you know, with this talk, the advantage that I had is because we are just trying to achieve quantum supremacy. You know, the thing that we are programming the quantum computer to do is in some sense incredibly simple, right? It is like a randomly chosen sequence of operations. You know, and then all the subtleties are about like how do you do statistics on the outputs to, you know, make sure, you know, to check that you did it correctly, and how do you know that it was hard for a classical computer to spoof the result, right? But if you want a quantum computer, you know, and actually this is already enough for like my application of certified random bits, right? But for most of the useful applications that you would hope for from a quantum computer, whether that means simulating quantum physics and chemistry, whether that means you know, factoring, you know, breaking cryptography, whether that means getting the square root, you know, Grover type speedups for optimization and machine learning problems, you have to do a much more precisely choreographed sequence of operations to your qubits. And that brings us to the whole topic of quantum algorithms, which is the field that I've mostly worked in for the last 20 years, right? And it is a, you know, it's an enormous subject. It is, you know, just, you know, rivaling at this point, I would say, the enormity of the field of classical algorithms, right? But, you know, maybe what I should say is that there are different levels of abstraction, right? So, like, as theorists in this field, we tend to just work at the highest level of abstraction that we can, of just, you know, proving that a quantum algorithm exists to solve a certain problem with a certain type of time scaling, right? And, you know, just like there are tricks for classical algorithms, there are many tricks that have been developed over the years for designing quantum algorithms. Okay, some of the most famous are what's called the quantum Fourier transform, which is at the heart of Shor's factoring algorithm, and which basically takes your exponentially large vector of amplitudes and performs a discrete Fourier transform on that vector, okay, and in order to extract periodicity information, which then, for reasons of classical number theory, you know, lets you factor numbers. Okay, Grover's algorithm uses a different technique that is called amplitude amplification. Okay, and there are several other, you know, sort of quantum algorithm design techniques, which again, you know, I teach an entire course about, or you could go to my homepage and, you know, read about how some of the quantum algorithms work, right? That's a whole other enormous topic, okay? Beautiful topic, you know, really worth learning about, you know, in my unbiased opinion, okay? But, you know, but then, even after you know the algorithm, there's still the challenge of converting it into the specific sequence of gates to be applied to these qubits, right? So there's like actually programming, writing code, and then compiling that down into a sequence of quantum gates. So those are all the problems of quantum software engineering. which there are a bunch of companies that even in advance of having the devices, they're working on those problems. And there actually are already a bunch of quantum programming languages and quantum compilation tools that you can download on the internet and play around with if you would like to try them out. That basically just take classical programming languages and extend them with some quantum primitives, like, apply this gate, this unitary transformation to this qubit, that then you can use to build up primitives like this quantum Fourier transform or amplitude amplification that I mentioned, that then let you do things like Shor's factoring algorithm or Grover search algorithm. So that was about the best I could do in 2 minutes for your question, but if you want to ask me offline, then you can.
Okay, Scott,
All right,
I think you've
sure.
done us
All right.
You might have more competition in the future.
Okay.